We address two main problems of robot perception: predicting observations from state and tracking robot state from observations. The contributions in this work include a novel forward model for predicting RGB images, and a framework for using both inverse and forward sensor models in tracking tasks. Let's begin with the problem of predicting observations. Given a new vector of joint values, we would like to generate an RGB frame of the corresponding robot pose from a given viewpoint. Many state-of-the-art techniques for image generation attempt to produce images directly from low-dimensional state. The images in these cases typically contain many artifacts or produce blurry renditions. We propose a deep forward model, KNN Flow, which instead learns to modify existing nearest neighbor images to produce new robot poses. Here we demonstrate prediction of 6-degree of freedom robot poses in simulation. The KNN Flow model uses a single nearest neighbor and is compared to both GAN and deconvolutional networks. Our network contains a parametric component which takes the current state and nearest neighbor vector and warps the nearest neighbor image to a new pose. The non-parametric component contains a KNN module for nearest neighbor selection. Each branch produces independent predictions, which are then weighted to produce the final image. We also test our approach on real-world robot data. Next, we address our second problem, tracking the state of the robot directly from images. Given a sequence of captured images, we can track the state by directly mapping from observations using an inverse sensor model. This can be done simply by training a convolutional network on collected data. However, we can also use a forward model for tracking state. Any generative network can also be used directly for filtering the state, without any fine-tuning on this new task. We can construct an extended Kalman filter by first modeling our state as a Gaussian belief distribution and using the mean for prediction. We can then officially compute the Jacobian in a layer-wise fashion. This provides a correction to the state distribution, and a transition model is used to propagate the belief distribution to the next time step. We compared tracking frameworks on real-world robot trajectories. The inverse model has been trained for this specific task and can actually accurately track the state of the robot. Although the forward models have been trained for image prediction only, they are still able to track the state of the robot using an EKF framework and an initial prior. Thank you for watching, and please come visit us at our poster session.